All right, in this video, we're going to look at problem number 4. It says find the area of each surface, and part A is the cylinder of radius A and height h. And while we certainly don't need calculus to compute the surface area, it's nonetheless a good illustration of what we developed in the last video on surface integrals. Okay, so from the table, we have the parameterization of the cylinder. Okay, and notice here, V, which is just the z height, is going to vary from 0 to h because the height of the cylinder is said to be h. Okay. And by the way, for a problem like this, you can just, if you're looking at a surface from the table, then just quote the results in the table. Okay, that's including this parameterization and the magnitude of that normal vector that we're going to need to compute the surface area. So those are all things you can just quote directly from that table. You do not have to derive them from scratch. All right, so let's go ahead now and look at the differential surface area element ds, right? That's just the magnitude of this normal vector, which is just the cross product of the tangent vectors tu and tv. And we have our dA, which is just du dv. And we derive that the magnitude of this cross product vector is equal to just a, right? That's just the radius of the cylinder. So we just get ADA for the ds surface area element. And so for the surface area then, right, as we discussed in the last video, that's just the integral then of just ds itself. And so then I just uh, uh, put in the magnitude of that cross product, and I have my dA, and this integral now is over the rectangle R in the UV plane. Okay, so I have my bounds on U and V, right? This is just my A coming from that calculation we made for the cylinder, and this all comes out to just be 2 pi AH, right? We're just integrating the constant A here. It's really simple. And this certainly is an agreement with what we would have gotten without calculus, right? This is just the circumference of this circular cross section of the cylinder, so 2 pi times the radius times the height of the cylinder. All right, cool. So now how about part B? We're looking at a hemisphere of radius A. Okay, so you can again just take the parameterization from the table. Be a little bit careful here since we're looking at a hemisphere. We want to let u, which is the angle phi in spherical coordinates, to vary from 0, not to pi, but to pi over 2, right? So when u is 0, we're along the positive z-axis, and then when u is pi over 2, we're in the xy plane, okay? And then v, the polar angle, which is just really theta, right? It's still going to vary from 0 to 2 pi. All right, so again, from the table, we derive that the magnitude of this cross product vector was a squared sine u. So again, you can just quote that, and then we have our bounds for u and v, and pretty simple integral again. You wind up getting 2 pi a squared, which is an agreement with the formula for the surface area of a sphere. Right now, for a full sphere, it's 4 pi times the square of the radius, which for whatever reason I always remember the volume is 4/3 pi times the radius cubed, and the surface area is just the derivative of that, so it's 4 pi times the square of the radius. And since we're looking at a hemisphere, it's just going to be half that, so 2 pi a squared makes sense. All right, cool. And now let's go ahead and look at the last one up here. We're looking at this portion of the cone z squared, which is x squared plus y squared, and we're letting z vary from 1 to 2. So again, the parameterization just comes from the table. And v, which is z, okay, that's going to vary from 1 to 2. U varies from 0 to 2 pi. And so here we derive that the magnitude of that cross product vector was the square root of 2 times v. Okay, so we're going to be integrating from 0 to 2 pi for u and from 1 to 2 for v. Again, simple integral. This comes out to be 3 pi times the square root of 2. All right, well, that is going to do it. Thanks so much.